Hello guys, how are you? It's teacher Yolanda here. Welcome to our session 23. For this session we're going to be using our content areas and that's it. Get ready for our science lesson of today. It's going to be interesting. Get your materials please. So, look at this. Do you recognize this? Of course, it's our home. We used to watch this right around here. We can identify that we're watching at Africa. Yes, here's Madagascar. And here's Antarctica. Another pronunciation of Antarctica, it's Antarctica. Yes, that's more of an American pronunciation though. What do you think? Is this a correct way to look at our planet? What's your impression? Is this photograph correct? Of course it is correct. But what do you think about the axis of our planet? The answer is that this picture is wrong. Our planet is not like this. Our planet is tilted. What's the meaning of tilted? Like this. Now, this is a correct representation of our planet. The axis of our planet is tilted. That means está inclinado, like the Pisa Tower. Have you seen it? It's tilted, it's leaning. So this is our axis. If we pay attention, we can see that the globes that we have sometimes in the offices, the planet is also tilted. Why? Because the rotation axis of our planet is not straight. Actually, our planet has more movements rather than the rotation and translation movements. Let's talk about them. Look at this. Here we have our tilted axis. The axis is not here. Yes. Having the axis here would be a mistake. Yes. The rotational axis of our planet is like this. It's completely tilted. And when our planet rotates on its rotational axis, when a part is facing the sun, that part is what we call day, and the opposite away from the sun is called night. But I bet you remember all of these from your science lessons in Spanish, don't you? But what you may not have seen in your science lessons is the following. Our planet has more movements rather than rotation when it comes to the axis. If you take a top, what is a top? A top is un trompo. If you take a top, you can see that when the top is rotating on its axis, it doesn't stay still, it dances a little bit. So our planet has exactly the same thing. As it rotates on its own axis, it dances a little bit. The movement is not steady. So here we have the rotation movement. The rotation movement just does this like a clock sense, right? But it has two other movements. It has precession. What is precession? Precession is this thing. Look at that. It rotates, but it also moves this way. So it's going like this, in this motion. And while it does that, it also shakes. It shakes a little bit. What is the shaking movement about? The shaking movement is called nutation. Nutation is this kind of movement our planet does while it's rotating on itself. So again, our planet has these two deviations, which is around 23.5 degrees as it rotates from the elliptical pole. Pay attention, this is the North Pole and this is the South Pole. These are not the geographical ones, but these are also the magnetic ones that we're talking about. Don't worry, later on in our class I will show you a video about this. Today we're going to watch some videos and make some summaries about all of these movements of the Earth. Now let's look at the translation movement of our planet. Again, our rotational axis is tilted and we have to pay attention about it. We have different movements according to the different seasons in the hemisphere. What is a hemisphere? The north of our planet and the south of our planet. That's what we call the North Pole. The South Pole, well, the North Pole is in the northern hemisphere, taking the equator in the center as half of our planet, and from the equator down, the southern hemisphere. Yes? So look at it. Our planet, besides doing the rotation, the nutation and precession, it's doing the translation movement. So that gets us 4 movements in total of our planet. The translation is the elliptical movement that it makes around the sun. But here we can see that that gets us, depending on how close, how far and how tilted it is towards the sun, our 4 seasons. So we have summer on the North Pole, which is around June the 20th and 21st, but at the same time it's winter in the South Pole. How can that be possible? Look at it. What is the reason of that? The reason of that is how tilted the axis is. Because in this part, the sun is hitting more directly to the north, while in the south, even though it rotates, the heat, el calor, the heat of the sun doesn't hit on the southern hemisphere. Now let's look at autumn. Autumn in the northern hemisphere, and in the southern hemisphere we have spring. It is on September the 22nd or the 23rd. On the northern hemisphere is winter, and the southern hemisphere is summer. This happens on December the 21st and the 22nd. On March the 20th or the 21st, we have a spring on the north hemisphere and autumn on the southern hemisphere. This is depending on 2 factors. Again, one is how tilted the axis is, and the second factor that we have to take into consideration is the elliptical shape. How close or how far we are from the sun at some point of the year. So now let's pay attention to our translation movement, because the translation movement is also responsible for having Antarctica as the coldest place on Earth rather than the North Pole. So most of the times we tend to think that our planet goes around the sun like this, and just like this, and that's the only movement it gets. Well, guess what? That is incorrect. Our translation ellipsis is not a circle. It's an ellipsis. That means that it's an irregular shape. It goes round the sun, but it's not to the same distance of the sun all the time. So I try to make this scheme. Actually, the sun will be something like that. No, something like that, I guess. And the earth will be something as tiny like this. That will be the correct size. But for the purpose of this illustration, I'm going to put the sun, let's say, this size. Now let's enlarge our planet. Can you see Mexico? Remember that this is not the correct shape. We have to tilt it. And now let's make it smaller, really small, so we can play with it. So how would the translation movement be like? The translation movement would actually be something like this. Can you see? In this position, the Earth is closer. And in this position, the Earth is the furthest. So, pay attention. In this movement, what's happening here? In this movement, right now, the sun is hitting the northern hemisphere. So what is that? That movement is exactly summer. So that means when our Earth is the furthest, what is the furthest? The furthest is lo más lejano. When it is the furthest from the sun, it is summer for all of us. That means that our summers in the northern hemisphere and spring in the northern hemisphere, it's hot, but we are really away from the sun. Look at that. As our planet starts moving, oh well, let's talk about this. And then on the South Pole, what is it? It's winter. So it doesn't receive as much of the sun as needed. And not only it doesn't receive much of the sun, but it's the furthest from the sun, so it is cold. And then it doesn't receive the light of the sun, so it's really cold. If we were talking about now, this part, now this is the moment in which the South Pole receives the light, but it is too close to the sun. And for now, this is our winter. It's winter, we don't receive enough light from the sun, but we are close to the sun. So that means that it doesn't affect us very much. So again, the summers in the southern hemispheres are hotter because they receive the sunlight and we are closer. This is winter. It is cold, but not that cold because we are close to the sun. Whereas the opposite, here we are receiving the sunlight directly on the northern hemisphere. So it is hot, but not extremely hot because we are further away from the sun. While in the southern hemisphere, they don't receive enough sunlight and it is winter. And that, kids, is one of the reasons why Antarctica is the coldest place on Earth. So, let's move on to the differences between the Antarctic and the Arctic regions. Just looking at it, of course, this is the South Pole of the planet and this is the North Pole of the planet. But look at it. Can you see one simple difference? Yes, look at that. The Antarctic is mainly surrounded by water, the Antarctic Ocean. And now look at the Arctic. The Arctic is closer to the continents. Look at that. This is Alaska in the north of Canada. This is Greenland. Here we have the UK. We have Scandinavia. And we have Russia. Look, over here is Japan. And this is the Pacific Ocean and the Atlantic Ocean. Can you see? That is also one of the reasons why the Arctic is hotter, because the continental masses are closer to it, while the Antarctic is mostly surrounded by water, the ocean. Look, here we have the south of Chile and Argentina. Here we go Australia, but it's too far away, and this is the south of Africa, but again it's too far away. Now let's talk about some of the comparisons between the Arctic and the Antarctic. So, Antarctica or Antarctica is in the South Pole, while the Arctic is in the North Pole. Antarctica is the coldest, driest, and windiest desert in the world. So if we think about it, the biggest deserts in the world are in the southern hemisphere: the Gobi Desert, the Sahara Desert, and Antarctica are the biggest deserts in our planet. And all of them are in the South Pole. Why? Because of the tilt of the rotational axis and what we saw. Remember, in the southern hemisphere, the hot is hotter and the cold is colder. So, in Antarctica there are penguins, and it is a continent. What does that mean? It means that it is an island, it's a continent, it's actually bigger than Australia. It's a really big continent. And it's covered with a glacier, yes? But in the North Pole, we have polars, igloos, and in the Arctic. That means that we have people living there, like the Inuit, and like many other people in the north regions of Russia and Scandinavia. In the Arctic, we have owls, walruses, caribou, and wolves. Lots of animals because there is a little bit of grass in the North Pole. Just very little of it is just ice. Most of it has a little bit of grasslands. The Arctic is in the North Pole and it's slightly warmer than Antarctica. I wouldn't say slightly, it's like 20 degrees or more of difference, which is a lot. On the worst days, of course. And here in the center of our Venn diagram, we have some similarities. Which are the similarities? Well, both of them have got seals, both of them have got icebergs, both of them are uninhabitable, they have freezing temperatures, and they have dry, cold weather. What does dry mean? It means that it doesn't rain a lot, it doesn't snow a lot, it's just cold. There are not even clouds. Why aren't there many clouds? Well, because there is not much evaporation, so most of the clouds that we can see over here are actually traveling clouds from other regions. The same as the water goes around the planet depending the cold and the hot temperatures, the same happens with the air. And actually it's so intertwined. The temperatures of the water depend highly on the temperatures on the air. So all of the weather of the planet depends on the ocean's temperature. So if they are uninhabitable, what about the North Pole? We have Inuit, we have people from Russia, but what about the South Pole? Who lives in the South Pole and why? Well, here's the answer. This is the only habitable place in the South Pole. And guess the name of this place, kids. This is the International Scott Amundsen Station. Do the names ring a bell? What's the meaning of do the names ring a bell? ¿Le suena? Yes, ring a bell. Scott Amundsen. Yeah, they are the first men to arrive to the South Pole. Do you remember our session on Scott and Amundsen? They were the explorers, the one of the race to the South Pole. We read about them before. So, the United States government and the government of other countries decided to make a station there just for research. We saw it in the text. Do you remember that they even have a chef? Well, this is a station from the outside. Here is the first part of the Scott Amundsen station. In the beginning, it was a dome. What is a dome? This half circle figure. The problem, as you can see, is this. The ice. Can you see this mountain of ice? So imagine they had scientists here during the summer, but as you know, the winter is the harshest winter in the world. What's harshest? El más cruel. So it practically all the winds carry the snow around. Remember, it's one of the windiest places on earth. And why is it so windy? Because there's nothing around to stop it. There's no mountains, there's no forests. All of the mountains are underneath the snow because it's the biggest glacier in the world. So what can we infer? All the wind moves the snow, and suddenly all this dome was buried under the snow. So when the scientists wanted to get out, they had to dig all the snow all around to get the scientists outside from here. So later on they realized that building a dome was one of the biggest mistakes they could have ever done. So basically this is the dome area, which is now not used. It is used during summer, but it's not very used during winter. And they decided to build a second station and forget about the dome. Look at it. This is the finished station. It is really, really, really big. And look at it. Here we have the geographic South Pole. What is that? We will talk about it later. Here we have at front of the station all the flags of all the countries which have contributed to the station throughout the years. Sadly, the Mexican flag is not there. Now, let's pay attention to the station. Why is the station better than the dome? First of all, it's divided in 4 main buildings with some stairs on the back to go out in case it's necessary. And the key of success for this building is actually this engineering poles that we have here. Exactly this. All of these things, guys, actually go up and down. So the complete building is built on poles that lift the building taller and taller and taller and taller during the winter. So it doesn't matter how much snow is moved by the wind, the building just grows up. So it is never buried under the snow. It is actually one of the best buildings in the planet. It's a master of engineering. And there is also a very interesting documentary of National Geographic on YouTube where you can see how they build it, because trust me, it was a challenge to build this, because remember, machines get cold, so cold that they cannot work, so they had to build it in some incredible ways. This is a design. Again, imagine that this is the level of the ground, but as you can see, all of these poles get down, 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 all the way to the top of the mountains. And this is the reason why there is a South Pole station, but there is not a North Pole station. And you may say, but why is that, teacher? The reason why this happens is because obviously there is a continent under Antarctica, but under the Arctic there's nothing, there's only water. So there is no way they could make a building without rock underneath it. But the first thing for building this station was actually digging holes so deep that they were kilometers deep. So they could get all of the poles attached to the top of the mountains underneath them. Now look at that. The geographic North Pole, 90 degrees north and 90 degrees south. What is that? Have you got any ideas? Why does it say the geographic North Pole? The North Pole is geographic, isn't it? What does it mean? Well, shocking news, guys. There are 2 North Poles and 2 South Poles. Pay attention. This is what we call the geographical South Pole. Remember that we have meridian lines, yes, and we have also some horizontal lines in our planet, but they are imaginary lines. You have seen this in your Spanish classes. So the problem with these imaginary lines is that they are straight as possible. We have the Tropic of Cancer and the Tropic of Capricorn, and we have in the center the equator. But what happens with these lines? Again, these lines are imaginary. So if we take a compass or a transporter, what we will call this is 90 degrees, right? It's like a straight angle, right? So 90 degrees to the north is a geographical meridian, is what we imagining in our heads that is the north of our planet. And the South Pole is a geographical meridian of the South Pole. Yes, but again, that's only in our imagination, guys. What about the other poles? The other poles are the magnetic poles. Remember that our rotational axis is not like this, it's like this. And what keeps our planet spinning are many forces. First of all is the gravitational attraction towards the sun, which is the biggest mass in our solar system, and that's why we are orbiting around the sun, because gravity attracts us to the sun. That is why we have the translation. But what about the rotation? What's the matter with rotation? Why do we spin on ourselves? Clearly, have you ever seen 2 magnets coming together with the same charge? They repel each other, they go away. So imagine that this is positive and this is negative. That is what keeps the planet spinning round and round, because it is repelling the magnetic forces all the time. And that's the reason why we have 2 poles. This is the rotational axis, this is positive, this is negative, and it keeps the planet spinning. This is the magnetic North Pole, and this is the magnetic South Pole. And if, of course, it varies, but it varies just a little bit. While the geographical meridian, for example, in the South Pole, they have to move it every day. Why? Because remember, all Antarctica is covered by ice. It's the biggest glacier in the world. So what's the matter with glaciers? Glaciers are moving. So that means that the Scott Amundsen Station and the South Pole, the geographical sign, it's moving every year. So every year they have to move it a little bit because the glacier is just walking towards the ocean. That's why the building of the Scott Amundsen station, it's not in a fixed place. It is walking toward the ocean every year. In 1,000 years or even more, it will reach the shores of the continent. Talking about the magnetic things, we have another great discovery to make about our planet. This thing over here. What is that thing? Isn't that strange? Well, kids, what we're looking at is the reason why there are auroras. What are the auroras? Remember that the auroras are the northern lights or the southern lights. Remember that borealis means north and australis means not north. And that was the reason why Australia was called Australia, because it's very at the south. So look at this. This is our sun. Sometimes we like to think about our sun like a pretty little star, but it's an enormous star, the biggest object in our solar system. And I want you to pay attention to this. And this. And this. And this enormous thing. All of these things that we're looking at are explosions. Remember that all explosions need combustion. So this means that all of these are dangerous things. Imagine these things breaking loose. At some point, these storms get too big that they break from the sun and they start traveling towards the planets. I'm sure that all of you have heard about the ozone layer. The ozone layer protects us from the UV rays from the sun, that is some radiation from the sun. Those are photons and light. But what happens when this storm breaks loose and travels the galaxy? The ozone layer cannot protect us from that. So, recently it's been discovered that our planet has another layer, and that is the magnetic layer. The magnetic layer looks like this. It is more or less like an apple shape, can you see? All of these are magnetic fields. These are also in charge of the rotation of our planet. All these magnetic fields help us to protect from the solar wind. Yes? So, when a snowstorm releases solar wind, the solar wind travels around the solar system towards the planets. And what protects us is the magnetic field of our Earth. That field is transparent, we cannot see it, it's invisible, because our eyes are not capable of watching magnetic force. But as you can see, it has a failure here and another failure here. What's that? That is the magnetic North Pole and the magnetic South Pole. So the solar wind travels, and these barriers, which are the Van Allen belts, that's the name, the Van Allen belts, try to protect us from the solar winds. But it absorbs all the particles that come from the sun, and they move towards the North Pole and the South Pole. And when the particles of the solar wind touch our atmosphere, they create tiny explosions. And that solar wind making explosions on the North Pole and the South Pole is what we call the auroras. So, pay attention again. This is the Van Allen belts. As you can see, here is the failure. We have the magnetosphere. The magnetosphere is the magnetic layer of our planet. It has some parts. The outer part is called bow shock. The next one is the magnetopause. This, that looks like an apple, is a magnetosphere. And when the solar wind attacks our planet, it expands. And as it expands, it creates like a tail. And that is called the magnetotail. And here we have the Van Allen belts, which are the names of our magnetic layer. Thanks to that, we are not fried by the solar wind. And when they reach the failures, las fallas, in the magnetosphere, look at this. It looks like wind. Why? Because it's wind. It's wind from the sun. And it is making explosions in our planet. That's how the auroras are created. All of this is solar wind hitting our atmosphere. And here in our planet we mostly watch it green and a little bit of red. But guess what? All the planets have a rotational movement, so that means that all of the planets also have magnetic fields and they have a magnetosphere too. And also, when the solar wind hits the other planets, they also have auroras. So that means that not only the Earth has auroras. Here we have an example of an aurora in Jupiter. We have the Earth's aurora and we have Saturn's aurora. Can you see? The aurora in Jupiter is blue, in our planet is green, and in Saturn is red. Why is that? The reason is because our atmospheres, the air in each planet, has different elements. And depending on the type of elements, it's the color of the explosion of the solar wind. That's why in Jupiter is blue, because the elements in the atmosphere of Jupiter lights the aurora blue. In the Earth, the explosions look green with a little bit of red, and in Saturn's is always red. And that happens in many, many systems around our universe. So I hope you've enjoyed our science lesson. Today we're going to watch some other videos and we're going to watch them with subtitles because I wanted to make a summary of those videos. These videos are explaining many of the things that we saw today, and we're going to have a tiny quiz to answer about those videos. So, see you in a few minutes. Bye!